The Earth's atmosphere. This thin veil of gas keeps our planet warm and shields us from harmful radiation from space. It gives us the air we breathe and controls the climate. Without it, life as we know it wouldn't exist. But Earth is not the only celestial body with an atmosphere. Planets, moons, even stars can be surrounded by layers of gas, each with unique properties. An atmosphere reveals a lot about the conditions on a given celestial object. And in some cases, its chemical makeup may even provide evidence of life. That's why scientists are paying close attention to these delicate layers of gas in their search for life beyond Earth.
What does the term atmosphere actually mean? Well, it refers to any gas envelope surrounding a celestial body. We understand the Earth's atmosphere very well because it was created many billions of years ago by gas emitted from volcanoes. Today, it consists largely of nitrogen and around 20% oxygen. The reason that this gas envelope hasn't escaped into space is that the Earth's gravity holds it in place. That's why all large planets with strong gravity are able to retain an atmosphere, while smaller moons and even some smaller planets have lost theirs over time. What matters for us is that life leaves behind traces known as biomarkers in planetary atmospheres. Two key indicators are methane and ozone, which points to oxygen. And that's exactly what makes studying the atmospheres of exoplanets so exciting.
When Earth formed around 4.5 billion years ago, it was a glowing sphere of molten rock surrounded by toxic gases released from deep within the planet. This early atmosphere was composed mainly of water vapor and carbon dioxide, along with traces of carbon monoxide, methane, and nitrogen. As the Earth cooled to around 500 degrees Celsius, water vapor and carbon dioxide remained the dominant components of its atmosphere. As temperatures continued to fall, water vapor began to condense, clinging to ash particles released into the atmosphere by volcanic eruptions. The result was a relentless rain that engulfed the entire planet. With the gradual cooling, the formation of the Earth's crust, the presence of liquid water, and a suitable atmosphere, the essential conditions were in place for life to emerge and endure.
It protects us from cosmic radiation that would harm us, and it protects us from UV radiation. But it also serves to balance out the temperatures on Earth. It provides for a certain amount of material transport on Earth. It serves to supply us with energy, namely the oxygen that we take in when we breathe. In this respect, the atmosphere performs a variety of functions that maintain biological life. This is also why we believe that a planet's atmosphere is absolutely necessary to sustain biological life as we know it.
Over billions of years, the Earth's atmosphere has undergone continuous change. Uninterrupted rainfall led to the formation of the primordial oceans, and at the same time, it washed carbon dioxide and sulfur out of the atmosphere, leaving nitrogen as the dominant gas. Then something remarkable happened beneath the surface of those early oceans. Around 3.5 billion years ago, in the Precambrian era, the first traces of life appeared. Simple bacteria-like single-celled organisms known as prokaryotes. These early ancestors of today's blue-green algae began harnessing the sun's energy. Through photosynthesis, they produced sugar from water and carbon dioxide, releasing oxygen as a byproduct. Over time, it began to escape into the atmosphere. Photosynthesis has been enriching our atmosphere with oxygen for around 2.5 billion years.
It's believed that oxygen was produced relatively early on. Perhaps even at the time when there were methane-producing bacteria, there were possibly already organisms that produced oxygen.
Die Sauerstoff erzeugt haben, aber dieser wurde sozusagen verbraucht.
But that oxygen was consumed, for example, through volcanic offshoots of iron, carbon, sulfur, and hydrogen in particular.
Und Wasserstoff insbesondere.
And it was only after oxygen had saturated those components that the production of oxygen actually increased the amount of oxygen in the atmosphere.
Von Sauerstoff in der Atmosphäre stattfand.
Compared to the size of our planet, its atmosphere is astonishingly thin. It's often compared to the skin of an apple. If Earth were to shrink to the size of an apple, the atmosphere would be no thicker than its peel. Today, this fragile layer is made up primarily of nitrogen, around 78%, and oxygen, about 21%, along with traces of argon, carbon dioxide, and other gases. A thin protective shell wrapped around a small ball of rock.
I'm a geophysicist, which means I could tell you the Earth's radius to the nearest kilometer, how thick or thin the Earth's atmosphere is. I'd seen satellite images beforehand, and yet I wasn't prepared for what awaited me. I think that's what we humans call the transition between knowledge and understanding. I knew all this beforehand, but I didn't understand it. At that moment, I understood that we live on a small, blue, rocky sphere, which is really small by any standard. And surrounding that small sphere is this much smaller, much thinner, delicate blue atmosphere that looks as if you could blow it away with a single breath.
The size of Earth plays a crucial role because gravity is the only force holding its atmosphere in place. Not only does it provide the air we breathe, it also regulates temperature and protects us from asteroid impacts and harmful radiation. Remarkably, the Earth's atmosphere is also self-cleaning. During thunderstorms, highly reactive hydroxyl radicals are formed. These molecules help break down pollutants like carbon monoxide or nitrogen oxide into compounds that can be washed out of the atmosphere when it rains.
Es wird so als Waschmittel der Atmosphäre.
This is known as the detergent of the atmosphere. So it's a very, very reactive radical that reacts with all kinds of other gases and substances and pollutants and can remove them from the atmosphere. In this sense, it's a net producer of water in the middle atmosphere.
Produzent von Wasser in der Mittelatmosphäre.
This means that more water vapor comes out of the middle atmosphere than goes in through this oxidation of methane together with the hydroxyl radical.
Das ist eine ganz interessante Geschichte.
As methane is increasing, there's also an increase in water vapor in the middle atmosphere, which in turn affects the recovery of the ozone layer.
Ozonschicht.
The Earth's atmosphere is made up of 5 main layers, with the lowest 3 being the most dense. The first of the lowest layers, the troposphere, extends from the Earth's surface to a height of around 15 kilometers. This is where all the weather events occur. Within the troposphere, temperature decreases with elevation, on average about 6.5 degrees Celsius for every 1,000 meters. Next up, above it, lies the stratosphere, extending up to around 50 kilometers. Here, temperatures rise gradually as the ozone layer absorbs much of the sun's ultraviolet radiation at an altitude of 10 to 30 kilometers, creating heat in the process. The stratosphere holds very little water vapor, yet under extremely cold conditions in the polar regions, clouds can still form. Pearly, iridescent structures made of tiny droplets of sulfuric acid with water and potassium nitrate molecules attached. When temperatures drop low enough, they crystallize, creating stratospheric clouds. Next comes the mesosphere, which reaches up to around 85 kilometers. Here, both temperature and air pressure drop significantly with altitude. At the top of this layer, average temperatures plunge to a chilling minus 90 degrees Celsius.
In the lower part of the atmosphere, including the mesosphere, which means up to an altitude of around 80 kilometers, the temperatures in the atmosphere are still relatively moderate, somewhere between minus 50 degrees Celsius and plus 30 degrees Celsius. However, that changes abruptly in the thermosphere above. Temperatures there rise to as much as 900 degrees Celsius. But this is also where the International Space Station and most satellites fly. So you might ask yourself, why don't they burn up? The answer is because the density of the atmosphere there is so low that the small amount of heat that is transferred is negligible and of no practical consequence. And that's why they don't burn up. The exosphere begins above the thermosphere. It's the transition into interplanetary space.
The International Space Station and most satellites circle the Earth at an altitude of around 400 kilometers. Even at that height, the atmosphere is still present, though incredibly thin. Up there, a single air molecule can travel up to 100 kilometers before colliding with another one. But despite being so sparse, these molecules still create drag, just enough to gradually slow down the space station's orbit. As a result, the ISS is constantly losing altitude. To counteract this, docked space capsules have to fire their engines regularly to boost the station back up. Otherwise, the ISS would eventually fall back to Earth and burn up in the atmosphere.
It is very interesting that the space station's loss of altitude due to the residual atmosphere is almost unpredictable. It depends on the density of the residual atmosphere at this altitude, and that depends on the thickness of the atmospheric layer. This, in turn, depends on the solar wind on that day. Solar wind is a stream of particles striking us from the sun. It heats up the Earth's atmosphere from the outside, and on a day with strong solar wind, the atmosphere becomes thicker in this area. This means that during days or months with strong solar radiation, the space station loses much more altitude than when solar activity is weak.
The farther we move from Earth, the thinner the atmosphere becomes. Its outermost layer is the exosphere, beginning at an altitude of around 500 kilometers. Here, gas particles begin to separate and stratify according to their atomic mass. Above 1,000 kilometers, only the lightest gas, atomic hydrogen, can be found. The outermost boundary of the exosphere isn't sharply defined. The transition into space is gradual, but it's estimated that it reaches about 10,000 kilometers high. In this distant region, lightweight gas molecules can drift away from the Earth's gravitational field simply by traveling fast enough. But if these gas particles are ionized, electrically charged, they move along the field lines of the Earth's magnetic field within the magnetosphere, unable to escape the planet's influence. To better understand the interaction between Earth's atmosphere and space, NASA's GOLD and ICON missions are studying the ionosphere, a region in the upper atmosphere where solar radiation excites atoms and molecules, making them electrically charged. The probes are collecting the data to improve predictions of space weather, solar activity that can disrupt satellite communications and GPS systems on Earth. The ionosphere is also where one of Earth's most mesmerizing light shows takes place, the aurora borealis, or northern lights. These glowing curtains of color are created when charged particles from the solar wind collide with the magnetosphere, an event that continues to fascinate us.
We were at an altitude of about 400 kilometers. That's just about the transition from the green part of the aurora to the red part. In other words, the transition between nitrogen and oxygen. And we flew right through it, intermittently. Everything was green below us, everything was red above us. And you look out and all you can think is, that is amazing. It's unbelievable that you're right in the middle of it. As a child, I could never have imagined that I would one day be inside an aurora.
From the space station, the Earth's atmosphere appears to end abruptly, a sharp boundary separating our planet from outer space. But that impression is deceiving. The outermost layer, extremely thin and composed mostly of hydrogen, is called the geocorona and stretches far into space. The solar probe SOHO detected traces of finely distributed hydrogen as far as 630,000 kilometers from Earth, well beyond the orbit of the Moon. It's a very thin veil of gas, with only around 70 atoms in 1 cubic centimeter of space. Still, by that definition, even the Moon is within the Earth's atmosphere. Nevertheless, the geocorona is so thin, it's practically indistinguishable from the vacuum of space.
Vacuum. What do we exactly mean by this? A vacuum is nothing more than a volume in which there is absolutely nothing, not even gas particles. The closest approximation that can be produced in the laboratory contains around 1,000 particles per cubic centimeter. In interplanetary space, there are about 20 particles per cubic centimeter, and in interstellar space, which means between the stars, there is 1 particle per cubic meter. Now you might ask, why doesn't the vacuum of space simply suck away the Earth's atmosphere? That's a misconception, because actually vacuum cannot suck anything whatsoever. The only thing that happens is that particles tend to expand into free space. But the Earth's gravity holds these gas particles back, and that's why the Earth's atmosphere remains in place. By the way, I'm often asked, is it really true that an unprotected human body bursts in the vacuum of space? No, that doesn't happen. It doesn't burst. What happens is that the blood in the body boils. This causes small blood vessels to burst. This leads to blockage, a collapse of the circulatory system, and then loss of consciousness within 15 seconds.
In his science fiction masterpiece, 2001: A Space Odyssey, which premiered in 1968, director Stanley Kubrick imagined a chilling scenario. Without the protection of a helmet, an astronaut is forced to expose himself briefly to the deadly vacuum of space. As he opens the hatch, air escapes into the void. The resulting sudden decompression causes the moisture in the remaining air to condense, forming a visible fog, a detail Kubrick got right. Even a partial vacuum can create air bubbles in the body, which can cause small blood vessels to burst. But if the exposure lasts only a few seconds, the damage is temporary. The blood vessels collapse again, and the astronaut survives.
The biggest problem is probably that because there's no pressure, the blood automatically starts to boil. A liquid that's not under pressure boils automatically. If you were to enter the vacuum of space, the fluids in your body would start to boil, especially your blood. And that would cause you to die relatively quickly. In other words, within a few seconds. Of course, it's also cold in space. You'd cool down over time. But because you're really in a vacuum, you don't cool down so quickly. So you'd survive the cold of space a little longer.
The fewer gas molecules in a given volume, the better the vacuum. On Earth, high-performance pumps can create vacuums with fewer than 10 million molecules per liter. By comparison, interstellar space contains less than 1,000 particles per liter. The reason lies in gravity. Gas molecules are drawn towards large masses, and so most gases are concentrated within galaxies. But the space between them isn't empty. In fact, absolute nothingness doesn't exist in our universe.
If we look very closely, the vacuum of space is not actually empty. Something's always brewing there. Particles are constantly being created and destroyed. That's backed up by a physical law. It's Heisenberg's uncertainty principle. It exists in the so-called energy-time variant. It tells us that you can very well violate the conservation of energy, one of the fundamental principles of physics, if the violation only occurs over a short enough interval. And in violating the conservation of energy, you can turn energy back into particles, E equals mc squared. So energy is a mass equivalent, and that's why a particle can flash up. And if it's only for a very short time, you won't even notice it. Now we believe the vacuum consists of particles that are continuously created and destroyed. The vacuum sort of bubbles, but it's bubbling away so quickly that we can't observe it.
The space between the stars is not empty either. Scientists call it the interstellar medium, a vast, diffuse mixture of hydrogen, helium, dust particles, and radiation. It surrounds the stars and galaxies like an atmosphere of its own. Powerful cosmic events, such as a supernova, the explosive death of a massive star, can compress the interstellar medium and send shock waves rippling through the galaxy. These waves can reach distant regions, influencing the birth of new stars and shaping the evolution of entire galaxies. The interstellar medium is also where countless chemical reactions take place, reactions that lead to the formation of new molecules.
What about the planets in our solar system? Do they have an atmosphere? That depends. Let's take Mercury. It's so small, it's never had an atmosphere. Mars is rather a borderline case. It's a bit too small to maintain an atmosphere. That's why it lost it over the course of billions of years. The gas planets Jupiter and Saturn are clear. The name says it all. They have a lot of gas, of course, but no solid surface. Not ideal for life. Venus is a very special case. Its atmosphere is very hot, namely 450 degrees Celsius on the surface, which is why life cannot develop there. However, in the higher layers, it gets cooler and cooler, so there just might be primitive life up there.
Our neighboring planet Venus is nearly the same size as Earth, which is why it's often called our sister planet. It is wrapped in a dense, permanent layer of toxic clouds. Its atmosphere is composed mostly of carbon dioxide, creating an extreme greenhouse effect. This has turned the planet into a scorching inferno, with surface temperatures soaring above 450 degrees Celsius. Under such conditions, life is impossible. On top of that, Venus's thick atmosphere exerts immense pressure on the planet's surface.
The atmospheric pressure on the surface of Venus is about 90 times higher than the atmospheric pressure on Earth. Together with the fact that the atmosphere of Venus consists almost entirely of the greenhouse gas carbon dioxide, this results in a temperature of around 400 degrees Celsius on the surface of Venus. We can't imagine biological life there. But the higher layers of Venus's atmosphere have temperatures similar to those on Earth. So you could imagine life, biological molecules that are in the highest layers of the atmosphere and have formed lightweight or primitive life forms.
Given the extreme conditions, researchers have ruled out the possibility of life on the surface of Venus. However, the situation may be very different higher up in its atmosphere. Scientists suspect that life may well exist in the gaseous layers surrounding our neighboring planet. This intriguing possibility has brought Venus back into the spotlight, with several research missions in planning.
The question is highly speculative, because surviving in the atmosphere is difficult. It's not just a matter of maintaining the right temperature. It's also about the fact that you need resources. And it's about the fact that you, for example, need a surface where these cells can grow. These are all exciting aspects of research on Venus. And hopefully there's a real possibility that life might be capable of migrating from the surface into the atmosphere.
Venus remains one of the most mysterious worlds in our solar system. It's almost identical in size to Earth, with only slightly less mass and a similar composition. and yet it still followed a completely different evolutionary path. To better understand this dry and hostile planet, the European Space Agency ESA is preparing an ambitious mission. Envision is set to launch in the early 2030s.
In this case, the proximity to the Sun means that water can no longer condense. On Earth, water can condense and rain down again, but not on Venus. And the early Sun had very high radiation intensity, and not just in the wavelength ranges in which ozone now forms. It thus subjected the water to photolysis, splitting it into hydrogen and oxygen. And at the prevailing high temperatures, the hydrogen's velocities then, in turn, exceeded the escape velocity of Venus, and it left Venus, and so Venus basically dried up.
At almost the same time as the European mission, Venus will also be visited by a U.S. research probe. The NASA mission Da Vinci is primarily concerned with the atmosphere of Venus. The probe is a flying chemistry laboratory that will descend through the planet's atmosphere to its surface. Samples are to be taken from the various layers of Venus's atmosphere and analyzed. Once on the ground, the Scout will have achieved its purpose, as all the relevant data will already have been collected and transmitted during the flight through the atmosphere. Scientists at NASA's Langley Research Center have developed a far more extraordinary concept. They are proposing a manned visit to Venus. Researchers are to spend a good month cruising above the planet in an airship within the atmosphere. Eventually, according to scientists Dale Arney and Chris Jones, a permanent human outpost could be established in the atmosphere of Venus. A concept that sounds very much like science fiction. And it probably is.
I think it's really important in space travel to have a visionary perspective, to think not just about the next step, but about the step after that. And so this concept where you could perhaps set up stations over Venus, floating space stations or floating atmospheric stations into research, I find that totally fascinating. This planet has so many secrets waiting to be revealed. There are active volcanoes, a dense atmosphere. We can't even get in there, but maybe we could observe it from above. So I think it would be exciting. If someone offered me the chance to fly there for 6 months to do research, I would do it without the slightest hesitation.
Mankind has always been fascinated by our other neighboring planet, Mars. Its atmosphere is thin, with just 1% of the density of Earth's atmosphere. But researchers know that it wasn't always like this. Traces on Mars suggest that the red planet once had a completely different appearance. Researchers assume that Mars, with temperatures around the freezing point, has a cool but humid past. Mars probably once had an atmosphere that was dense enough to allow liquid water on its surface. But it could not hold this gas envelope over the long term. Because Mars has no protective magnetic field, the solar wind struck its atmosphere unimpeded and hurled it into space over the course of many hundreds of millions of years.
But we know that there used to be more water, much, much more water, and that there were also lakes. We can even talk about oceans, at least to some extent. And why are conditions there so different nowadays? We only have speculation and theories. None of this has been proven exactly. It's possible that there's still liquid water on Mars, but that would require higher temperatures and higher pressure. And that in turn means pressure. In other words, if you go deeper into the interior, you could imagine, for example, that there are caves or channels of some sort at a depth of maybe 10 or 20 kilometers. And if you were to find liquid water there, you might also find life. So it remains a very interesting area of study. But with today's robotics technology, it's just very difficult to find water there at all, if it even exists.
Liquid water and a dense atmosphere could indicate that life once existed on Mars. With the low gas pressure that its thin atmosphere now provides, any water there would evaporate within seconds. Today, the surface of Mars is as dry as dust. However, water in frozen form can still be found on both polar ice caps. And researchers even suspect that there is liquid water deep below the surface, so-called subglacial lakes. These subterranean water reservoirs could contain the very extraterrestrial life that scientists are searching for so intensively, even if it is perhaps only algae or bacteria. For this very reason, Mars is the most extensively explored planet outside of Earth. So far, however, scraping the Martian ground has only uncovered some ice deposits. Still no trace of life.
Mars is an extremely attractive goal for us because it was once a potentially habitable planet. There was a dense atmosphere, maybe water. Maybe. There was water on the surface, and you can still see traces of it. What happened? Why is it now a desolate, empty planet with a very thin residual atmosphere? How can we prevent the same thing from happening to Earth?
The Moon is much closer to mankind than Mars. It may be a dead world, a world without air, but to be perfectly precise, our Moon does have a kind of atmosphere, a so-called exosphere, a thin veil of gas that, on a cold, moonlit night, descends onto its surface. It contains helium, neon, hydrogen, and argon, but in very small quantities. The mass of the entire lunar atmosphere weighs only about 10 tons. This means that it is so thin that there is little or no interaction between its constituent particles.
Formally speaking, the Moon has an atmosphere, the so-called exosphere, but in practical terms, it's altogether negligible. It consists mainly of hydrogen, and this is due to the fact that the solar wind constantly drives hydrogen atoms into the surface, which then outgas during the day and form this very thin atmosphere. None of the moons in our solar system have an atmosphere, with one important exception, and that is Titan. Why is that? Titan is slightly smaller than Mars and has no magnetic field. Nevertheless, it has a very dense atmosphere that is larger and thicker than that of the Earth. Why is that? It's because there are methane clouds, and they shield the heat from the outside, exerting a kind of anti-greenhouse effect that keeps the surface very cold, minus 180 degrees Celsius. And because it's so cold, the hydrocarbon oceans do not evaporate.
With a diameter of 5,150 kilometers, Saturn's moon, Titan, is larger than Mercury. It is the second largest moon in our solar system. Titan's unique atmosphere is what makes it so interesting. Titan has no magnetic field of its own, but the magnetic field of nearby Saturn gives it a certain amount of protection from the solar wind. A closer look at Titan offers the panorama of a strange world that nevertheless seems familiar to us. A fascinating world with a cloudy sky and landscapes reminiscent of Earth, rivers, lakes, fjords, mountains, and barren plains.
The liquids you see are not water, they're hydrocarbons, methane, for example. The lakes consist of liquid methane or liquid ethane. These are hydrocarbon compounds. These are actual carbon compounds that can be considered the basis for life. And it has an atmosphere that provides for a certain exchange of material, just like on Earth. So that alone is interesting. The only problem is that it must be very cold there for methane to become liquid or for ethane to become liquid. They have to be around minus 150 to minus 200 degrees Celsius. This in turn means that chemical processes occur very slowly, and that means that if there were life there, it would certainly be very simple and perhaps need a little more time to develop.
Titan's gas shell consists mainly of nitrogen, around 95%. It also comprises around 5% methane. It is this methane that gives the atmosphere its orange color due to the effects of sunlight. Another reason why researchers are so excited about this atmosphere is that it may resemble the primordial atmosphere of our Earth. This is because nitrogen dominates only in the gas shells of Earth and Titan. Accordingly, researchers hope to gain more knowledge about our own primordial atmosphere by studying Titan's atmosphere. In addition, the average temperature on Titan is just under minus 180 degrees Celsius. And so it could well be that many of the chemical components that served to create life on Earth are deep frozen and thus preserved on Titan.
This raises the question, could life also be based on liquids other than water? Can protocells also form where chemicals could then be concentrated to form DNA or RNA strands? But the basic question that remains is whether it's too cold there to drive these reactions fast enough to give rise to evolution that leads to RNA or DNA or equivalent structures. And this question is exciting and still completely open.
And so its atmosphere makes Saturn's moon a fascinating object for researchers. At the same time, this atmosphere has long obscured its surface. Titan was therefore considered one of the most mysterious objects in our solar system. In January 2005, the ESA probe Huygens succeeded in landing on the surface of Titan during the Cassini-Huygens mission. The descent through the atmosphere took 2.5 hours. In the process, the explorer transmitted spectacular images back to Earth. The mother probe Cassini also mapped a large part of the surface of Saturn's moon with its infrared and radar sensors.
The search for life on worlds such as Titan, where there are ethane and methane lakes and no liquid water on the surface, may also give us insights into what other traces of life we should or could discover on planets orbiting other stars.
To further explore Titan, the U.S. space agency NASA is planning another mission to Saturn's moon. The project is called Dragonfly. After arriving on Titan, a drone, a so-called multicopter, will explore Titan's surface. The rotorcraft, with 8 rotors, will land repeatedly, take samples, and examine them for prebiotic chemical and geological processes. Processes that may have also existed on early Earth. The researchers want to learn more about how chemistry could become biology.
Atmospheres are normally transparent. In this sense, even our Sun has an atmosphere, with the important difference that its gaseous envelope can reach temperatures of up to 1 million degrees Celsius. On planets, the atmosphere serves as a metabolic medium for higher land creatures. They deposit their metabolic products in that atmosphere. Referred to as biomarkers, such metabolic products are an important indication of life on a planet. This is precisely the reason why the search for life on exoplanets today focuses on these biomarkers. And the James Webb Space Telescope was built specifically for this purpose.
December 25, 2021. The successful launch of the James Webb Space Telescope marks the beginning of a new era. Exploring the early phases and evolution of our universe is one of the main missions of the James Webb Space Telescope. However, observing stars and planets within our own galaxy also constitutes a large part of the research. And in that context in particular, peering into the atmospheres of extrasolar planets.
The telescope enables us to study relatively small Earth-like planets and to analyze their atmospheres in greater detail for the first time. There was no telescope capable of this before. It was possible to analyze atmospheres, but only on very large planets that were definitely not conducive to life and were also very close to their star. I believe that the James Webb Telescope will provide us with the first clues here. I also suspect this because we're talking about the question of all questions, is there life elsewhere in the universe? I can't think of a bigger question that we as humanity want to answer. And for that reason alone, I believe that researchers will do everything they can to answer this question with the James Webb Space Telescope.
With its infrared instruments, the telescope examines the atmospheres of alien planets. The aim is to identify chemical compounds as products of organic life that cannot otherwise be detected. Biomarkers such as methane and ozone are particularly easy to detect in the infrared. The instruments now make it possible to study alien atmospheres using spectroscopy. Take the atmosphere of WASP 96b, for example. Using its highly sensitive instruments, the telescope analyzed light that had passed through and been filtered by the distant gas giant's atmosphere. It turned out that the planet's gaseous envelope contains water vapor. However, the analysis failed to detect biomarkers in the chemical fingerprint.
We now have the James Webb Space Telescope that captures the light from these small planets and then brings it to me on the computer screen. And here I can look for traces of life in the atmosphere of these planets. And that's the combination of oxygen from a reducing gas like methane. And I'd also like to see traces of water, because all life on Earth needs water. In other words, this light flying through space is a message encoded with information about the composition of the air on another planet, and whether it takes biology to explain its presence.
Our Milky Way consists of over 100 billion planetary systems, and the James Webb Space Telescope now offers researchers the opportunity to precisely study the atmospheres of extrasolar rocky planets. Over 200 Earth-like planets have been discovered outside our solar system so far. By examining their gaseous envelopes, researchers hope to find the biomarkers that could provide the decisive clue to possible life.
Das läuft dann darauf hinaus.
This then boils down to looking for so-called non-equilibrium gases, which means gases that are not in thermodynamic equilibrium with the atmosphere. Thermodynamic equilibrium in this context would mean that the gases simply react chemically, and I can therefore always predict a certain amount of these gases. Methane is an example of this in the Earth's atmosphere, as it's present 6 orders of magnitude more than it would be if there were no life. We'll be looking for these gases, these so-called non-equilibrium gases. And Carl Sagan tried to do this by looking at the spectra of the Earth's atmosphere during the flyby of the Galileo mission and saying, if I look at it now, and I don't know anything about the atmosphere, can it tell me anything about whether there is life there or not? And then he came to the conclusion, yes, this and this and this point to it. So that's the difference between detecting the presence of conditions conducive to life and actually detecting life.
Spectacular results are not far off. In the atmosphere of the exoplanet K2-18b, researchers have found evidence of DMS, dimethyl sulfide, an organic compound containing sulfur. DMS produces the typical smell of the sea. It is formed by macroscopically small algae, the phytoplankton that swim around in the uppermost ocean layer. So far, only biological sources of dimethyl sulfide are known. K2-18b is a so-called super-Earth. It's 124 light-years away and probably largely covered by water. If we can confirm the presence of DMS on the planet, there would be a chance of extraterrestrial life there. Using data from the James Webb Space Telescope, a team of European astronomers investigated the atmosphere of another gas giant. WASP 107b is about 200 light-years from Earth and located in the constellation Virgo. By shining a light through its cloudy atmosphere, researchers discovered water vapor, sulfur dioxide, and even clouds of sand in a dynamic atmosphere.
At the moment, this search is at the limit of what is technically possible. This means that it is incredibly difficult to filter out these tiny signals from traces of molecules in a planet's atmosphere. But we've now embarked on the path that will lead us to these traces. Now comes the Extremely Large Telescope in Chile. Then comes the Habitable Worlds Observatory and the Life Observatory, which are currently in the design phase. With this new generation of telescopes, it's not just the atmospheric signals that we can detect, but we can also look down to the ground level, if you like, and see any patches of green, purple, red or yellow that could indicate biopigments.
The atmospheres of Earth-like rocky planets are of the greatest relevance in our search for life. The TRAPPIST-1 planetary system has 7 rocky planets and is currently the best candidate for studying their atmospheres. The researchers focus TRAPPIST-1c. This exoplanet is almost the same size as Venus and also has a similar temperature. However, observations indicate an atmosphere that is very different from that of Venus. By analyzing the heat emitted by the planet, researchers conclude that it has at best a thin gas shell with a minimal carbon dioxide content. The measurements are also consistent with bare rock in the absence of any significant atmosphere. So in the search for the formation of life, it represents yet another miss.
Red dwarf stars are active at the beginning of their lives, much longer than the Sun, and there is a concern that they might blow away part or all of their atmosphere because they are so active. We're currently researching precisely this phenomenon. But the problem is that it takes time. It's very difficult to interpret whether, for example, there's no atmosphere on a given planet, or whether the atmosphere is simply different, so that we just can't see far enough into it. Because an atmosphere that's completely optically dense, in other words, you can't see through it, will look the same as if there's no atmosphere at all.
Researchers are not only studying atmospheres, they're also looking at how planets lose their atmospheres. Astronomers can observe such a loss of gas of heretofore unrivaled proportions on the gas giant HAT P32b, 950 light-years away. Trailing the planet are 2 unusually long tails of helium and hydrogen. Calculations show that more than 1 billion kilograms of helium flow away from the planet every second. To put that in perspective, on Earth, some 50 grams of helium leave the planet's atmosphere every second. Despite the tremendous speed at which the planet is losing its atmosphere, it will probably take around 1 billion years before its gas envelope is completely expelled.
Yes, planets really have to fight to retain their atmosphere. And unfortunately, Mars lost that battle. Over the course of billions of years, it has almost completely lost its atmosphere. It's different with the Earth, which exerts greater gravitational pull and can therefore hold on to its gas shell. Nevertheless, it's continuously losing a small quantity of hydrogen. But that doesn't matter at all, because seawater is constantly replenishing this hydrogen. In addition, the Earth is perfect in that it has a stable atmospheric stratification that mainly depends on ozone. Basically, higher life requires 2 conditions: a dense atmosphere and exactly the right temperature range, somewhere between 0 and 40 degrees Celsius. And that's why all the exoplanets that are exactly the right distance from their star and have the right temperature and size are like Earth, the best candidates for finding life. And biomarkers will show us the way.
atmospheres surround planets, moons, and stars. Their outer edges mark the transition into space. Astronomers are especially captivated by the gas envelopes of extrasolar planets. They're searching for signs of life within them. And if life can be proven to exist elsewhere, that life must exist everywhere in the universe.